There's a rock on a volcanic island in Indonesia that looks like nothing special. Gray, grainy, the kind of stone you'd kick out of your way on a hike. But that rock, called bauxite, is the reason the phone in your pocket exists. It's the reason your laptop powers on, the reason your car has wiring, the reason satellites stay in orbit. And here's the paradox. Almost none of the world's electronics run on Indonesian metal directly. Instead, this rock travels thousands of miles, gets torn apart at a molecular level, and comes back out as something so different you'd never guess they were related. Why does a lump of red-gray stone from one island chain control a trillion-dollar global industry? To understand that, you have to follow the rock from the ground to the circuit board. And it starts with something surprisingly simple. Dirt that isn't really dirt at all. Bauxite doesn't look like ore. It looks like clay, reddish-brown, soft enough to crumble in your hand. But underneath that unglamorous appearance is one of the highest concentrations of aluminum oxide found anywhere on Earth. It forms only under very specific tropical weathering conditions, heavy rainfall, high heat, and millions of years of chemical breakdown of volcanic rock. That is why so much of it comes from equatorial regions like Indonesia, Guinea, and Australia. Once mining crews strip away the topsoil, excavators dig into shallow deposits, usually just a few meters deep, and load the raw bauxite onto trucks. From there it moves to a processing plant, where the real preparation begins. Workers and automated systems run the ore through crushers that break it down into smaller, more uniform chunks. Then it's washed to remove excess clay and organic material, because purity matters enormously here. A single processing facility can handle over 10,000 tons of bauxite in a single day. A scale most people never picture when they think about where their electronics come from. Once the bauxite is crushed and cleaned, it's ready for the core transformation. And this is where things get genuinely wild. First, the ore is mixed with a hot caustic soda solution, sodium hydroxide, inside massive pressurized vessels called digesters. Temperatures inside these digesters climb to around 270 degrees Fahrenheit, and the pressure forces the aluminum oxide to dissolve out of the rock, while impurities like iron and silica stay behind as a reddish sludge. That is why this stage is called the Bayer process. After digestion, the liquid is filtered to remove solid waste, and what's left is a clear, aluminum-rich solution. At this stage, the solution is cooled and seeded with tiny aluminum hydroxide crystals, which triggers a chain reaction. Crystals multiply and grow, precipitating out of the liquid like sugar settling out of syrup. Once that happens, the crystals are collected, washed, and heated in massive rotary kilns at temperatures reaching nearly 2,000 degrees Fahrenheit. This step is called calcination, and it drives off all remaining water. What's left is a fine white powder, pure alumina. But alumina still isn't metal yet. It has to go through one more transformation. The alumina is dissolved into molten cryolite inside enormous electrolytic cells, and an electric current, sometimes exceeding 100,000 amps, is passed through the mixture. That electric current rips the oxygen atoms away from the aluminum atoms, a process called the Hall-Héroult process, leaving behind liquid metallic aluminum that sinks to the bottom of the cell. By the time it reaches the final stage, the transformation from dull rock to shining metal is complete, but the process isn't finished yet. Quality inspection teams test the purity of the aluminum, checking for trace contamination that could weaken its conductivity or strength. Any batch that doesn't meet strict industry standards gets sent back for further refining. The approved aluminum is then poured into molds, cooled, and cast into ingots, bars, or coils, depending on what it's destined to become. After that, it's shipped to specialized facilities where it's rolled, extruded, or drawn into wires, foils, and sheets, thin enough to be used inside circuit boards, phone casings, and battery components. From there, it enters the global logistics network, moving through ports, cargo ships, and distribution centers, before landing in a factory where it becomes part of an actual device. What started as a crumbly reddish rock on a volcanic island has become an essential ingredient in nearly every piece of modern technology. But here's the complication. This process is extraordinarily energy-intensive. Producing aluminum through electrolysis consumes more electricity per ton than almost any other industrial process on the planet. Some smelters run continuously, 24 hours a day, because shutting them down even briefly can cause the molten metal inside to solidify and destroy the equipment. That means aluminum production is tightly linked to energy prices and energy availability, which is why smelters tend to cluster near cheap hydroelectric or coal power. And that creates a hidden vulnerability in the global electronics supply chain. If a major bauxite-producing region faces political instability, export restrictions, or environmental regulation changes, the ripple effects can reach every factory that builds phones, laptops, and cars. Now zoom out. Indonesia alone holds some of the largest bauxite reserves on Earth, and in recent years, it has restricted raw ore exports to force more processing to happen domestically. That single policy decision sent shockwaves through global aluminum prices, because so much of the world's electronics manufacturing depends on a stable, predictable flow of this metal. One island chain's mining policy can nudge the price of the phone in your hand. That is the kind of hidden interconnectedness most of us never think about, because the paradox is invisible. We see finished, polished electronics, not the volcanic rock underneath them. And there's a downside worth sitting with. Bauxite mining and aluminum refining come with real environmental costs. The red sludge left over from the Bayer process, called red mud, is highly caustic and difficult to dispose of safely. Improperly managed storage ponds have failed before, causing serious ecological damage. Add to that the massive carbon footprint of electrolytic smelting, especially in regions still powered by fossil fuels, and you start to see the tension at the heart of this industry. The very metal that makes lightweight, efficient technology possible is expensive to produce in environmental terms. So the next time you pick up your phone, remember that inside it is a piece of a volcanic island that traveled through crushers, chemical baths, superheated kilns, and electric currents strong enough to power a small town. It is a strange, almost invisible chain connecting tropical rainforests to your back pocket. And as demand for electronics keeps climbing, so does the pressure on this fragile, energy-hungry pipeline. Will greener smelting methods catch up in time? Will new bauxite sources shift the balance of global power again? That question is still unfolding. If this kind of hidden industrial process fascinates you as much as it fascinates me, hit subscribe, because there are dozens more stories like this waiting to be uncovered. Drop a comment if you want to see how another everyday material makes its way from raw rock to finished technology. And if you learned something new today, give this video a like. It genuinely helps this channel keep making content like this. Thanks for watching, and I'll see you in the next one.